Hello everyone. Today I am going to discuss about Hall effect experiment. So let's get started. The aim of our experiment is to determine the carrier concentration in the given specimen of the semiconductor material and to calculate the Hall coefficient. Now let's look into the requirement of the experiment. Here in this experiment we require an electromagnet, the power supply for the electromagnet, constant power supply, multimeters, Gauss or Tesla meters, and Hall probe. Now let's look into the theory of the experiment. Hall effect was suggested by Professor E. H. Hall in 1879, that is way before the discovery of electron by J. J. Thomson in 1897. The Hall effect is the production of voltage difference across a current carrying semiconductor which is placed in a magnetic field perpendicular to both current and magnetic field. The voltage produced is known as the Hall voltage. Suppose a semiconductor carrying current is placed in a magnetic field with the direction of the field perpendicular to the direction of the current. Then a voltage is developed across the semiconductor in a direction perpendicular to the both current and magnetic field. This phenomenon is known as the Hall effect, and the voltage developed across this is known as the Hall voltage, which is represented by the Vh. Now let us see how the Hall effect works. For that, consider a rectangular conductor of thickness T kept in a xy plane. An electric field is applied in x direction using constant current generated so that the current flows through the sample. If W is the width of the sample and T is the thickness, if the magnetic field is applied along the negative z-axis, then the Lorentz force moves the charge carrier towards the y direction. This results in accumulation of charge carriers at the top edge of the sample. This set up a transverse electric field EY in the sample. This developed a potential difference along the y-axis is also known as the Hall voltage Vh, and this effect is known as the Hall effect. Now let us understand this using a schematic diagram. Here we have a rectangular conductor and here we have a constant current generator, and it produces a current across the conductor in x direction. Suppose it is the positive and this is the negative terminal. The current flows from the positive to the negative, while the electrons flows from the negative to the positive terminal, which is represented in the figure. So when no magnetic field is placed in the conductor, the current flows in the normal form, that is from positive to negative, while the electron flows from the negative to positive. So no net change occurs there. Suppose if we place a magnetic field in such a way that it is perpendicular to the direction of the current, it produces some distortions in the charge. Then a Lorentz force is induced and it makes the charge, or it makes the electron to drift towards one end of the conductor. The other end has the depletion region, or which have deficiency of the electrons. This is known as the Hall effect. While we take the sample, during the Hall effect phenomena, the concentration of electrons at one end is greater than the other end. So if we take the potential across this end, we see that there is a sufficient number of potential difference across the opposite end, that is in the y direction. So we can get the direction of the electron drift by using Fleming's left hand rule. Here B is the magnetic field, Jx is the current density, and the thickness of the semiconductor material, or simply the conductor, is given by T, and W is the width, and Vh is the Hall voltage which occurs during the Hall effect process. So when a current is made to flow through the sample material and the voltage difference between its top and bottom is measured using voltmeter, then the applied magnetic field is zero, the voltage difference would be zero. When we have the current flow in response to an applied electric field with its direction as convenient, and it is either due to the flow of holes in the direction of the current or the movement of the electrons backward. In both cases, under the application of the magnetic field, the magnetic Lorentz force occurs. That is, we have the magnetic Lorentz force Fl is equal to minus E into Vx cross Bz. That is, Vx is measured across the x-axis and the applied magnetic field is in the z-axis. This causes the carrier to curve upwards. Since the charge cannot escape from the material, a vertical charge imbalance builds up. This charge imbalance produces an electric field which contracts with the magnetic force and a steady state is established. The vertical electric field can be measured as a transverse voltage difference using a voltmeter. Along with Lorentz force, there is another force which occurs in the circuit, that is the electric force, which occurs in the x direction, which is given by E into EH. EH is the Hall electric field. In the steady state condition, the magnetic force is balanced by the electric force, which can be expressed as the both sum, that is E into EH is equal to minus E into Vx into Bz. That is, we equate the both forces in the equilibrium condition. Further, the current density is given by Jx is equal to NeVx. Therefore, we can take the Vx as 1 by Ne into Jx. Thus, on substituting, we get the Hall electric field EH is equal to minus 1 by Ne Bz into Jx. If we substitute minus 1 by Ne with a constant, which is known as the Hall constant, that is RH. RH is equal to minus 1 by Ne, which is inversely proportional to the density of charge carrier, and therefore we have RH is equal to EH by Bz Jx. This relationship shows that the Hall effect is proportional to both magnetic field and electric field. So the Hall coefficient RH can be written as Vh into D into Bz into Lx, where D is the thickness of the material. So that's all the theory we require for the experiment. Now let's look into the procedure of our experiment. So firstly, we have to switch on the Hall effect setup and adjust the current. Now we have to place the Hall probe in the magnetic field and switch on the electromagnetic power supply and adjust the current to any desired voltage. The VH and Vx voltage are measured using voltmeter. Measure the magnetic field Hy using Gauss meter. For each value of Hy, plot Ix versus Vx graph and calculate the slope, that is Vh by Ix, from which we can calculate the RH. A graph of Vh versus Vx is plotted and slope, that is Vh by Vx, is found, from which we can calculate the Hall angle, that is given by tan theta is equal to Vh by Vx into L by W. L is the length and W is the width of the semiconductor. So this is the setup, and this is the setup for the Hall effect experiment. Here we have the Gauss meter and the power supply for the electromagnet, which is connected to the electromagnet. So this current will produce a magnetic field in the electromagnet. So on controlling the current, we can control the magnetic field required. A Gauss meter is required to measure the magnetic field using a probe which is attached to the Gauss meter. Then the specimen or the semiconductor is connected to the constant current power supply, which shows the corresponding Vx and Ix readings of the semiconductor specimen, which is placed in the electromagnet. Now let's look into the observation and tabulations of the experiment. Firstly, we have to measure the magnetic field corresponding to the applied current. For that, arrange the setup in such a way that the a constant current is set up in the power supply and it produces some magnetic field in the electromagnet. Using the Gauss meter, place the probe in between the electromagnet and measure the obtained magnetic field. The different current ranges are noted as in the tabulation. Here we could see that at current 0.5 ampere, it produces a magnetic field of 520 Gauss. Similarly, for different values of current, the magnetic field is observed. Now all we have to do is set a magnetic field at constant using the current supply for the magnet, and we have to measure the Vx and Ix component from the semiconductor probe. For the measurement of the current, place the semiconductor material in the magnetic field produced by the electromagnetic in such a way that the magnetic field is perpendicular to the semiconductor specimen. Then, corresponding to that, note the Ix, that is current in the x-axis, in the reading of the constant power supply. Turn the knob to the voltage and measure the horizontal voltage or the Hall voltage, which is produced in the semiconductor. Using a multimeter, measure the voltage across the x-axis. This procedure is repeated for different current, that is, on changing the current of Ix, we can get the different values. So these values are as tabulated from the observation. The same procedure is repeated for another magnetic field. 4 to 5 readings are taken in the same manner. After tabulating the readings, now we have to plot a graph, that is between Ix and Vz, which would be a straight line as shown in the figure. We have to take the slope, that is dy by dx, so which produces and gives a slope. Correspondingly, we have to measure the volt we have to measure the Hall angle. For that, we have to plot a graph between Vx and Vz, and corresponding to that we get a straight line and the slope of which is taken, that is Vz by Vx is taken. Similar graph is plotted for different magnetic field. Now these are the readings. For different magnetic field, we have the thickness, that is 0.5 into 10 raised to minus 5. So these are the slopes of 4 different graphs plotted, and from which we can calculate the Hall coefficient RH, which is given by Vh by Ix into d by Bz. Here Vh by Ix is the slope which we get from the graph, and d is the thickness, with d is the here d is the thickness of the semiconductor, and b is the applied magnetic field which we have taken, which is converted into Tesla. So we get the mean RH or the Hall coefficient, which is about 0.0143. Now we have to find the charge carrier concentration, that is N. We have the formula R is equal to 1 by Ne. So we can get N is equal to 1 by RHE. RH is the Hall coefficient which we have calculated earlier. So the result is taken and calculated. Now we drew another plot for the Hall angle, which is given by tan phi is equal to Vh by W into L by Vx. Here W is the width and L is the length of the semiconductor specimen. So Vh by Vx is the slope of the graph which we have calculated using the plotted graph. So those slopes are tabulated corresponding to the magnetic field, from which we can calculate the angle tan phi. Taking the inverse tangent of the angle, we get the angle phi, which is the Hall angle. That is all about the experiment. Hope you all understand. Thank you.